what the initial conditions usually are. Let me write it. Projectile motion. Projectile motion.
Yeah. So are we on problem 50 right now?
No, we are on projectile motion.
Okay.
So
just in general.
The two information you gotta have to solve everything is the angle and the initial velocity.
Yeah.
Okay. So once you have the angle and the initial velocity as a vector, what you can do is, let me write it here, decompose. Yes. What does it mean? Thank you for correcting my English. It's a long time I don't live in the UK.
Like decompose to like take it apart?
Now, you decompose it along the axis. So you take separately.
So yeah.
You take separately Vy and Vx. Now, what is Vx equal to and what is Vy equal to?
Vx is cosine. So this is, wait, let me write. This is speed, right?
Yes, that's B.
Yeah, that's speed. Can we call this theta? Because that's what we usually use.
Okay.
Okay.
Why don't calling it Xi? Because it's complicated. Okay, let's go for theta, no worries.
Theta, yeah, like that's what our school usually uses for unknown angles. So yeah, so Vx is speed times cosine theta.
Correct. What about Vy?
What is, oh, yeah, and then V sine theta.
Okay. Now, second, what do? We use the so-called Galilean relativity. Galilean relativity. What does it mean? We study the two motions independently. Okay. Where do we start from?
What do you mean, like, where do we start?
Well, we have two axes. We gotta look at the y-axis and at the x-axis independently. So where do we start from and why?
Y-axis, because we know one of the acceleration. We know the acceleration.
Not only, but okay. Let me introduce then another question. So let's go on the y-axis. So what type of motion is it along the y-axis?
Vertical.
Just look at this.
Parabola?
How can it be a parabola along one axis? Come on, Anna.
Like,
along one axis. There are three types of...
down, vertical?
There are two types of motion. We have seen them last lesson.
Yeah.
One is linear uniform motion. The other one is linearly accelerated.
So it's linearly accelerating
motion. Yes. So along... Exactly. Along y, there is gravity. Are you already familiar with arguments like kinetic energy, potential energy, and so on, or not yet?
Not yet.
Okay, good. Because this type of problems can happily be resolved like in 2 steps with the argument of energy, but we'll do that. So along y there is gravity. Hence, how do we tackle this?
How do we tackle the fact that there is gravity?
How do we study the motion of the projectile along the y-axis?
confused by what you mean. How do we study it?
Okay, so let me somehow lecture and you will jump in where needed. So it starts with a velocity, going up. Then what it does, it slows down. And then what happens? It stops.
It stops, yeah.
Full stop. Why am I putting a full stop here? Because this time is exactly 1/2 of the ATA, so the estimated time of arrival, isn't it?
ATA. And estimated time like of arrival as in like the time it takes for the whole motion.
Exactly. And at this point, the parabola, so the idea that you had before that it was doing like this, at half of the time you are here, isn't it?
Yeah.
Good. What happens
we're
then?
At the highest
Exactly,
point.
exactly. At the vertex of the parabola. Now, what does it do?
No, it starts coming back down, so the velocity becomes negative, and it's accelerating uniformly with the rate of like gravity, the acceleration rate of gravity.
Okay, now Anna, this is a Nobel Prize question. What happens when you throw a stone just vertically up?
What happens when you throw a what?
A stone, just a big thick object. What happens?
There's air resistance.
You throw a stone up. What happens?
Like it goes up, it goes back down.
If you throw a stone up, what happens is you step away. Otherwise,
oh yeah.
It's not that trivial, you know. Like out of 10 pupils, 8 forget that things come back down for gravity. So it arrives there, it stops, and then it comes back down. What is the final velocity after the down part of the trajectory?
Like after it comes to a rest, it's going to be 0.
Yes, at the top, this is very good, and it is important to put it there. V equals 0, and this is important because it gives you the condition to find the time it needs to reach the vertex. After it comes back down, before doing this, what speed did it gain?
It gained like VF equals to VI plus AT, so it gained 9.8 times whatever time it took for it to fall.
Okay, so quick example. Let's see how much time you need. Example. So v0 y, so the starting upward velocity, e, let it be 5 meters per second. What is the final velocity along the y-axis? 3, 2, 1.
What is the final velocity?
Yes.
If it takes
Again,
3
3.
seconds?
No. I said the upward velocity is 5 meters per second. And I wish you to tell me the final velocity in 3, 2, 1.
0.
No.
I'm really confused.
No, you're not. That's just because you have never thrown a stone up and then got it to your head.
Yeah, like I haven't.
You haven't.
I'm throwing it forward.
So
a little bit.
The thing goes up. And what happens? It stops.
Yeah.
And then
it comes back down.
Okay. And how much time will it go down?
The same amount of time it took to go up.
So how long will it accelerate going down?
Like however much time it took for it to go up.
So what is the velocity at the end of the down part?
The initial velocity?
Exactly the same. Exactly the same.
I don't. Okay, I understand it, but I don't understand why. Like, is it because it was accelerating? Like, in one side it was negative, and in the other side it was positive.
You can call it like this, but you are too much mathematical for not for being a mathematical dragon. So, if it takes 2 seconds decelerating, it takes 2 seconds accelerating. The acceleration is the same. So the variation in velocity is the same.
Yeah.
Okay.
Oh,
In
wait,
a couple of weeks, I will be able to tell you the following sentence. Energy is conserved. So when you throw it up, it has some kinetic energy, which turns into something else, and then it turns down again into kinetic. So the speed at the end is the same. So good to know that. Okay. Out of this, we can determine the time 1/2. Hence the total flight as well.
Yeah.
Why do we need this total time?
Because the total time is how we're gonna figure out like the distance.
Yes, correct.
Yeah.
Correct. Bingo. So now we set the y-axis. Now let's go to the x-axis. What type of motion have we got along the x-axis?
It depends on how it's thrown, but it would be uniformly accelerating. Wait,
Oh, really?
If we're just throwing it just up, there is no motion.
Okay.
But if we like throw it forward, then it would be like uniformly accelerating, right? Yeah.
Okay. Now, let's draw a free body diagram. I love the way you love my active learning. So let this be a, I don't know, let this be a stone like this that you throw like this. So
Okay.
let's draw only the stone. Please draw the free body diagram.
Like draw the free body diagram of the stone.
Yes, exactly.
There is no normal force.
No.
No, because this isn't force, that's velocity.
Exactly.
So it's just this? Like
Exactly.
pressure.
Exactly, because it is always decelerating. Now, what direction is the acceleration having?
Like side, like it's that way.
Vertical down, isn't it? Okay, no, sorry, I didn't forget my last sentence. So this is the only force that we have. What is the acceleration that we have? Can you?
Negative 9.8.
Sure, negative 9.8. That's the force. Actually, no, that's okay. Okay, let's say that this is 1 kilogram, so we can happily do like that. So can you draw the acceleration here on this very FBD?
I don't know how to draw acceleration.
Oh, well, thank you. I love this way of interacting. So what is acceleration?
Okay.
What is this? I'm not mocking you actually. What is acceleration?
Like it's how much the velocity is increasing by.
Unit time. Yes. Do you know any easy formula linking acceleration and force maybe?
Force, wait.
Amazing. Yeah, that's fine.
No, but because we usually use like the second one.
Okay. You forgot two things though.
What?
This.
Oh, the vector arrows.
And what does that mean? That the acceleration is the very same force vector scaled by mass. And since mass is always positive in this part of the universe, it is just multiplied. So how to draw acceleration? It's the same. It's the same arrow, just longer or shorter depending on the mass.
And that's literally it.
And it's literally it. So if force is only vertical, acceleration is?
It can be used sideways as well.
Oh, really? How?
Well, not right now. Not right now. Right now, the acceleration is only vertical as well.
Why? Because there is only gravity acting. Because there is only gravity acting. Okay.
It's only the force, and the acceleration has the same direction as the force.
Yes.
Right.
So 90% of the is there the city band again? I can't hear it.
What?
Is there the city band again?
No city band.
Okay. Okay. 90% of the time along the x-axis you have a linear motion. Oh, sorry, let me leave it there. Just linear, not accelerated, because
no
the
force
exactly. 90% of the times, no acceleration along x. So once you have the time, the total distance, let's call it x final, is equal to what? To the velocity times t.
VIT. It's just VIT.
Exactly.
Right.
Exactly.
Okay. I think I understand. Yeah.
Now, a quick variation on this. How do we treat? I don't want the numbers. I just want the reasoning. Let's say that there is a rocket launched like this with, I won't make it very complicated because I could introduce like, okay, so the engine applies a force of a, I don't know, let's say 1 mega Newton, 45 degrees. Yes, mega Newton, 45 degrees.
Okay.
Exactly at the top of the parabola, it switches off.
Okay.
Can you give me a brief description of what happens?
Of what?
Of what happens? What's going on?
What's gonna happen when?
Yes, in this scenario, can you treat it, please? Can you study it?
Like, it would just be like this, and then it would go like down. Is that right? Because the force is constant, so I'm assuming that the acceleration will be 0 because the force is the same as the force of gravity, so the net force is 0 after the initial. No, that's off.
That's off. You are assuming too much.
Yeah. Wait, force is a meganewton. I'm bad with like the measurement of force.
Okay, yeah. By the way, if I don't give you the mass, it won't work a lot. So let's say that the mass of this thing is well, 10 tons. Oh, sorry. Yeah. Okay. I'm the scientist is me. Okay. So a ton is 10 to the third kilograms.
Yeah.
And a meganewton is 10 to the sixth newtons, like this.
So 10 to the 6th. Okay. So question.
The question is, think for 2 minutes. I'll take 1 minute off and then I'll come back. Just a second, please. The question is gonna be, treat this scenario the same way we treated the last one. I will be right back. Sorry.
You're back? Okay.
Yes, I am.
It's like, and at the top it switches off. Like, I don't.
You do. You do. Let's try again. You do, and you say, yeah, of course I do. So let's go back to the board here. Come on, it's okay. So let's go back here and let's look. First, decompose.
Yeah.
Okay.
So
What do we decompose now?
Vy, Vx.
Is the initial velocity given?
No, but the initial force is given. So
Only the initial force. So you see, I am just squeezing out and juicing out your mind because it's tasty. You apply the same technique just to another object. But does it make any difference? No, because it is a vector. And vector have components. And components can be decomposed along each axis. It doesn't really matter how much.
how much what?
How many axes you have. That can be done in nth dimension. I don't want to overcomplicate it, but the point is, you first decompose what? Force. And so here we go in and say 1. There is no velocity, so let's put it v0 equals 0. It starts from rest.
Yeah.
3, 2, 1, ignition. I like having happy classes. By the way, it's 9:30, so I usually lay down to sleep at this time. So I am a little bit keeping myself up as well. Now you are
Okay. I'll get that energy up.
exactly. So we decompose what? Forces along the two axes, isn't it? Yes. So what force can be decomposed along the two axes?
Like the horizontal and vertical applied force.
Yes, but how many forces are there acting? Always think about the free body diagram. You have the rocket here.
3.
3.
No, 2.
2.
No, 3.
3.
Because, like, sideways, up, and
how many forces are okay, draw the FBD. Let's start from the OBD. No, not the VD.
From the what?
FBD. Aspetta un momento, dopo te dici.
Oh, free body diagram.
Yes.
That's what an FBD is. Okay, well, there's always
Attenzione che così te lo rompo.
F, G.
You know, just you can just easy, okay, G or just MG, how you wish. It doesn't matter. Doesn't matter. Sorry, I am.
Okay, FG, and then yeah, FG, and then there's like FA applied.
Okay, FE engine. Okay, diga.
Yeah.
Hello.
Ok. Ok, gioca un poco, basta che non ti mi disturbi. Ok, sorry, this is the only interruption that we are going to have.
No, that's okay. That's okay.
Yeah, he is so cute. He is so cute. Okay,
What is he? Sorry.
that's fine. So decompose F. Now F's, because there are how many forces? At the
Multiple.
two, just two, not three, just two. So one is gravity, the other one is the engine. Let's decompose them, please.
Let's decompose the forces.
Yes.
Well, like into horizontal and vertical. Yes.
Precisely.
Yeah. So this here. Wait, it's 1 mn, 1 meganewton times cosine 45.
Capital. Otherwise, m is milli, which is 10 minus 3. And small n is number of moles.
Oh, okay.
By the way, are you dealing with chemistry as well, sooner or later?
No, not yet. Later.
Okay. I'm sorry, that's so funny. Okay, it doesn't matter.
Okay, it's okay. Now, okay. Mn and then Fy. Okay, there we go. And then is that?
Go on.
So that's the deconstructed vertical forces.
Yes.
And horizontal, yeah.
Okay. Now,
And now,
shall we treat gravity the same? Shall we decompose gravity?
do we not know gravity is 9.8?
Yes, but do we decompose it?
How do we decompose it further?
Easy. Minus 9.8 times minus 9.8 times the mass going down vertically, and what is the horizontal component of gravity? Let's call it like this, Fgx.
0.
Yes, as easy as that. We have decomposed it. Now, let's study the vertical axis.
Okay.
What happens along the vertical axis?
Well, there are two vertical forces right now. So we have Fy and Fg. So what we want to do is we want to find the net force, right? Yeah. So since we want to find the net force, we do Fy minus Fg. Is that correct?
It is. Well, actually, no. And there is a small moment, because to be actually correct, and I started to be picky, but this is what you and all the others want from me, you don't subtract them, but you sum them vectorially.
But it's going to be a negative force.
Doesn't really matter. There are no negative vectors. So you do the following. I suggest drawing, like this is engine and this is gravity. I don't know. Let's find out with numbers. So let's try with numbers, plugging numbers in.
Plugging numbers in?
Yes.
Okay.
Let's see what is done about.
Wait,
Just
I don't know how to plug meganewtons.
okay. Let's like a rule of thumb. If the engine force was was Smaller than gravity. What would happen?
It would go up.
If it is smaller than gravity.
Oh, smaller.
Yes.
Then it would just stay there.
Really?
Well, it would go down if it's not at rest.
Look.
If...
Look. I laugh because it is kind of funny, the picture that came to my mind. So this is the rocket, and there is not enough gasoline to push it up. But what will happen? The horizontal component will still be there.
So it would go forward and down.
Exactly. It's like shaking a cola bottle, piercing it on one side and putting it onto the wall. It does. That's what happens.
Yeah.
That's why I laughed. That's why I laughed. I have a pretty vivid imagination. Okay. Now let's go with meganewtons. So meganewtons is, so the force going up is how much? Well, 1 times 10 to the plus 6 Newton. While the force going, this is engine, gravity is how much? 9.8 times
10 to the power of 3.
So which means this is almost 10 to the fourth.
Yeah.
So the net force is 10 to the second power going up, right? So there are 100 newtons pushing up.
100 newtons of force.
Pushing it up. Now, for some reason, I can't see you anymore anyway.
Wait, what?
I can't see you. I don't know why the video is out. And it doesn't matter. I mean.
Wait, no, let me check this because that's weird. My Wi-Fi was glitching like a moment earlier, so maybe that's why?
That may be, yes.
Okay, wait. Let me see.
Okay, better.
I switched it. Can you see me now?
Yes, I can. Okay.
Okay.
Now, can we go on?
I think. Well, we know that we now know the force, the net force, and that's 100
newtons.
Yeah, that's 100 newtons. So we know the net force. So from that we can calculate the acceleration.
Mm-hmm.
And then 100 divided by
1000. Yes.
Wait, 0.1.
Thank you. Measurement units?
Newton. Meters/second square.
Yes. Meters per square second. Good. Tu poi mettiti un po' di calzetti, se non si fa dopo.
Vabbè.
Dopo ti posso qua ascoltare. Che bella puttana che hai visto.
Come si chiama?
Anna. No, te lo domandi dopo. Good. Now, what is our next step? What is our next step? What happens then?
So we now know the vertical acceleration.
Mm-hmm.
Do we calculate the horizontal calculation?
Let's analyze fully the y-axis and then fully the x-axis. Doesn't make any sense.
So now we calculate how much time it's going to take for it to like go up.
Yes.
So for the VIF, the final velocity, aka when it's at the top, it's gonna be 0. So it's VI plus AT. So 0 equals to 0 plus acceleration/time.
Yes.
0.1
Mm-hmm.
So, wait, I don't think this is right, because t would have to be 0.
Exactly.
Yeah.
Exactly.
So it's wrong.
Why is it wrong? The condition
Because
were just off because I pick it up from my mind. And the engine force is just too strong to stop. Because I told you, it switches
so
off.
never gonna stop.
It's never going to stop. At the moment, we don't have enough data to determine the half flight time. Hence, bye bye. I mean, it's just, and that's it. As easy as that.
Yeah.
But please, by the way, it happened to come out as a wonderful exercise. It is not wrong. It is just weird or odd, as you wish, because it is not the standard type of exercise that you have. Okay, good. What was this to be a part? Okay, let's say that we change the conditions and we find that after 10 seconds this engine switches off.
What if we find that out?
Mm-hmm.
So now what?
Let's suppose. What is our next step?
Well, okay, first of all, it's gonna take 10 seconds for it to fall down, right?
Mm-hmm.
Yeah, so it's gonna be 20. The whole entire trajectory took 20 seconds.
Mm-hmm.
And now we can find out our horizontal velocity.
Well, we had it. We have. Okay, go on. I don't want to insist because this is a great way to recap.
Okay. So the question right now, like, what are we looking for? Like, what are you asking me to find?
Well, all the rest. We checked the y-axis. Now we are to check the x-axis. Yes.
Yeah. Okay. So we can find the distance that it travels, like sideways.
Mm-hmm. Go on, please. Analyze it first. You have a brilliant mind. Use it.
Yeah.
Mm.
Okay. So free body diagram. There is no like on the x-axis, it's just going forward. It's going to be going forward at the same speed because there is no force acting on it, right?
Let's go back up to
There's going to be no acceleration.
Okay. Look at this. Sorry. Look at this.
Yeah. Oh, wait, never mind, because it's literally going to be accelerating the whole time. Or 10 seconds.
It's not the whole time. Because this is, I made it on purpose that it is not complicated, but it is structured in a way. So it is accelerating 10 seconds, and then what is it doing?
Accelerating for 10 seconds, and then it's just going to be continuing at the same speed as the final velocity.
Until
It falls down. Is that right? Yeah.
Yes, it is.
So
now let's quickly write an equation. Well, we can solve it. It's an exercise anyway, so.
Yeah, so now we know that time is 10, and we know that the force of this is mn.
Along x, it is accelerating.
So that would be mn, and mn is mn is 10 to the 6th, right?
10 to the 6th cosinus 45.
Let me figure that out.
It's square root of 2 divided by 2, which is 0.766, something like that.
7,700. Wait, no, wait, 700.
7.76, isn't it? Okay, well, whatever.
Points here.
Okay.
But yeah, 707.
You usually write it the scientific way, which means 1.45 e or 10 times 10 to the 1, 2, 3, 4. So in this case, it's.
I don't know how E works.
Okay, never mind. So this is well, we are starting some math as well, right? So this is the whole number. How much is this? This is 7.1 because we round it here up.
Yeah.
Times 10 to the 1, 2, 3, 4, 5. Got it?
Okay, got it.
Good. So it's 7.1 times 10 to the 5th measurement unit. Measurement unit.
10 to the 5th.
Newtons. We are talking about force.
Yeah, and that's the net force, so now we divide that by the mass.
Yes, so we divide it by 1 E3, which gives us 7.1 E2.
What is E?
E is exponent, so times 10 to the some power. Okay, okay. So 3, no worries. 3E2 means 300. Means 3 times 10 to the second power.
And E3 is 1,000?
Yes. And E6 is 1 million, and one E6 is 1 million. 2 E6 is 2 million, and so on.
Okay, I understand. Okay.
So now it's accelerating for 10 seconds, and then it is drifting for other 10 seconds. And we can go on, but before going down, I would like to ask you, after this, shall we go for exercise 49, which is the wedge accelerated with an acceleration of a like this.
Okay. Let's do that one, yeah.
Good. Okay.
Because I don't think, I think today might be better to spend, our 30 minutes extra, on physics, because I have the test coming up.
I completely agree with you. And by the way, I encourage you to shoot me questions. So since I hope you are going to prepare some more time, not only this lesson, use me. Just use me. I am at your service. Use me.
Thank you.
After 370 questions, I will ask your dad to feed in a little bit of cash. But until you are below 370 questions, no worries. The more precise you are able to give it, the easier it is for me to help.
I understand.
Good.
Okay.
Yeah. Let's stop it here because the rest is trivial. And let's go for question 49.
Could I run to the restroom real quick?
Please do that.
Okay. I'll be right back.
That's sure. So the wedge is accelerating. Gravity is acting on the block.
Yeah.
Is that all for the free body diagram?
Yeah, because there's normal force.
Mm-hmm. And what else? This is an acceleration going that way. But if there is an acceleration,
Going this way?
as well, okay, but before going that way, if there is an acceleration going right, it means there is what going right?
A friction going
No,
right?
there is a force going right.
Oh,
If there is an acceleration, it means there is a force. If there is no acceleration, there is no force.
yes.
Good.
Very true.
So let's be a little bit tricky, and let's say that we draw in green gravity.
Okay.
How do we draw the normal force of the plane as a reaction to gravity? I am half lecturing, but doesn't matter. We do it like this because we decompose gravity perpendicular to the plane and along the plane. I guess you knew that. And this is N, which is mg cos 35, isn't it?
Yeah.
Good. Now,
Sorry.
no worries. Now, what about the force pulling the wedge?
What about the force pulling the wedge?
Yes.
Like, what do you mean, what about it?
What is the interaction between these two objects?
It's going like this way. Is it not like this way?
If the wedge accelerates to the right for the
It's gonna fall down.
third Newton's law, the block is going to the left. So there is an anti-force like this, which will then be decomposed the same way.
And so we have to find the value.
The value of the horizontal force, I mean the force pulling the wedge to counter gravity.
Yeah.
Let me write it. So
But if it's accelerating, then it's not moving.
oh,
Wait,
really?
then it's moving, and don't we want it to not move?
Exactly. Because if we start the clock and the wedge is still, what happens?
If we start
Start the clock. I mean, we run the experiment. You know, we are ready, steady, go. What happens to the block? It falls down. But we don't want it to fall down. So we start pulling the wedge. So by pulling the wedge, the reaction of the block will keep it in place. Countering gravity. You may want to rewrite it or anything, I don't know. Come on, it's readable. It's readable.
Like, yeah, by pulling the wedge, the motion,
the reaction of the block will keep it in place. Okay, sorry.
Will keep it in place.
Yes, exactly.
Okay, there we go.
Countering gravity. Gravity. Countering gravity. Countering. Okay.
Okay.
And how much is that force?
How much is that force?
Yes.
Like, it will be the same, it will be the opposite of the force of gravity on this object.
Exactly. So how much is this one?
Negative 9.8 times the mass.
This is the reaction to the force of the wedge, not gravity. Gravity is easy. Okay, let's go by step. So how much is this one? Gravity pulling down. Let's call it Fg parallel.
Well, then it's just negative 9.8 times the mass.
No, times the sine of 35. Correct. And this is exactly what this must be. So this red thing here must be what? Must be must be F times what?
Fg, so time mg, mass times gravity, times sine 35.
That's gravity.
This is it negative.
We are pulling the wedge. What is the component along the slope of the force pulling the wedge?
What is the component along the force pulling the wedge?
What is the component of the force pulling the wedge along the slope? Let me draw it like this. So this is the wedge. This is the force pulling it that way, and we are asked how much is this one? If this is 35.
Is that not like sine 35 something? Because it's the same as this slope.
Are you sure?
Well, we know that this one is mass times gravity times sine 35, and normal force, that's cosine. Is it like the normal? No, it's not. So this force is a component of these two vectors.
It's decomposed along those ones. Yes.
Yeah. So
it is F.
This would be cosine.
Yes, cosine 35.
Cosine 35, yeah. Okay. I'm getting somewhere.
You are brilliant. I was not expecting, actually. This is, it's not extra hard, but it is really structured as a problem. So you're brilliant. And this is just our second chat. So we equate
I'm
this.
Be moving
Go on.
down to like the easier physics class for winter, so that's gonna be a lot better. I'm gonna have like a much easier time.
No, you're gonna have a much boring time.
No, because I'm failing. Like I don't have time for this.
Come on.
No.
You will want it. Just give me another month. You will throw everything away and will beg me to give you and send you more books. Okay. So we equate the two and write that MA cos theta. Instead of writing F, we write MA equals what? MG sin alpha. Sorry, sin theta. And
So
MA, this one is MA.
This is an A, right? Yeah. Cosine theta is mass times gravity. Let me write that down.
Yes, please.
Mass times acceleration. Cosine theta is equals to mass times gravity sine theta. Because it's these like two, right?
Yes.
Okay.
Okay. Now let's go to part B.
Yeah. There's more.
Yes.
Okay.
Happily, yes, there is.
Now V, if the acceleration. Wait, so did we find what the value of acceleration is?
No, we only need to plug in the numbers.
But for A, it says determine what value of acceleration will prevent the 5 kilogram mass.
Exactly. So we plug them in, hop, hop, and we find that A is equal to what? G sin theta over cos theta, which means 9.81 times the tangents of 35.
Okay. Okay. Now
Good.
for B.
B.
So now.
Now, part B, we assume an acceleration A to be 9.2 meters per second. And we ask, how much must the friction force between the 5 kilograms mass and the wedge be to keep it there? And does the friction point up or down?
Up. Because it's pointing this direction.
We don't know. First, calculate this one. Calculate this one.
9.81. I don't get where the 81 came from. I get the 9.8.
Okay, use 9.8. Doesn't matter. 9.8.
So negative 9.8 times tan 35. So negative 6.86.
6.86. Okay.
Yeah.
So what does it mean? If we move to the right with 6.86 meters per square second, the block will be we stay put.
If we move to the left.
To the right. Don't be fooled by signs.
Are we not trying to calculate this?
Yes, but we calculated it asking what is the acceleration that we gotta use to the left. Since they are gonna be the same, they are going to counter. They must counter. This one will be the same as this one, and we were asked what this must be, what the acceleration of the wedge to the right must be to keep it in place.
Okay.
Good.
Got it.
Now, that means that if we move it to the right with 6.86, the block will stay put.
Yeah.
What happens if we move to the right with a greater acceleration?
It will move down.
Really?
No, it will move up.
It will move up. So let's write it. This is greater than gravity pulling down.
Thus, it would move up.
So it will slide up. Hence friction, what side would it be?
On the other side.
Will go down.
Yeah.
You see, the first gut feeling would be, hey, it goes up because the block will slide down, but it is not, because we are pulling it too fast, and basically it will be like this.
And it's going up.
Exactly.
Yeah.
Okay. Now, let's quickly, the very last 10 minutes, try calculating the static friction force. We have talked about it last time, but
Calculating the what?
the static friction force.
Oh,
So
for this thing.
we want static friction
Yeah.
to keep it in place. How do we work?
If we want static friction to keep it in place.
Yes.
Well, the static friction must be enough to counteract the acceleration.
Yes.
Shouldn't. Yeah.
And the friction force is how much? Is
The friction.
the static coefficient times the normal reaction to the plane, which means static coefficient mg cos 35.
Wait, I don't get it. What is the static coefficient?
A number that tells you how smooth or not are two surfaces compared one to the other.
Okay, I understand.
So we have, I would like you to reason, but since we are slightly running out of time, I would like to take your hand and walk you through it. How does it look like?
That sounds good.
So we have an acceleration to the right of 9 point, how much was it? 9.2.
Yeah.
How much is the acceleration pulling up?
Against the 9.2?
No, because 9.2 is the acceleration vertically. And now we want this one. So
And now we.
for a right acceleration of 9.2, the force pushing the block up is 9.2 cosinus 35, sorry, sinus 35.
Sine 35.
Yes, sine 35.
Okay.
Full stop. This is diminished by gravity pulling down. Can you understand? Because there is the component of the force pulling up, since we are sliding the wedge too quick, but there is still gravity pulling it down, isn't it?
Yeah.
So the net force, is the one the friction must counter. That friction must
So as to keep the net force 0.
exactly must counter is ma cos 35 minus mg sin 35.
Minus mg sine 35.
Yes. This is to be, this is, well, there is no mention about the friction coefficient. So this is the friction job.
Okay.
So
This is the friction
job, yes.
Job, yeah. Okay.
That's it.
Yeah. I think that's about all we have time for.
Yes.
But okay, I understand a lot more things about friction, and especially just using the free body diagram. Thank you.
No, you're amazing. Just amazing.
Thank you.
You know, being a mentor, I had several pupils along the years, and it is always a pleasure to work with someone who is, you know, reactive, who is not to be pushed or kicked through the, okay, come on, please, hey, wake up, and so on. Great. Maybe it's the, you know, US atmosphere, maybe it's the earlier time of the day, I don't know, but still it is a pleasure. Okay, now I
I
will.
think it's the U.S. atmosphere because it's like that's exactly what my school is it's all like talking and collaborating. Like that's how my school learns. That's our teaching method. But so yeah, it's like very human contact, very like discussion, very discussion based.
Okay.
Yeah.
Okay. Nice hearing it.